Dissociation methodology. We no longer accept Gall's classification of mental organs, of course. We do not believe that there is anything in the brain that specifically represents something like secretiveness versus cautiousness versus amativeness. But we do accept the basic premise that guided his ideas, and that is that the brain is organized in terms of modular systems. And the question is, what is the proper methodology to identify these modules, given that we don't know what they are? We have to discover them through a scientific method. And the method that I'm going to be talking about here is known as dissociation methodology. And I'm going to be talking about neuropsychological evidence based on dissociations that allow you to draw inferences about modules or modular systems involved in various kinds of tasks. And the particular task that I'm interested in talking to you about today is reading aloud. So what is the modular organization, or what evidence can we get that the reading system is made up of mental modules or modular systems? And to begin, we of course have to have some kind of idea that we want to test in advance, so we have to get the idea from somewhere, and we typically do so by, in the same way that other sciences do, we have some sort of theoretical principle, theoretical guess, if you like, that drives our research. And I'm going to show you a particular idea, which is that we have a number of distinct components that are listed here in front of you that are involved in converting a printed word to sound. So we're starting at the very top of the diagram where print is written, and we're going down through a series of processing mechanisms to speech output, which is the pronunciation of the word. So if I give you a word like print, print, and you read it aloud, you're going through this system of processes. And the first stage of this mechanism is the identification of letters. And of course, it is a gross simplification to say that the complex visual processes that identify a squiggle on the page as a letter is simply encapsulated in one box. But we simplify, and that's how science progresses. We say, okay, whatever is going on there, we'll call it letter identification as a single component. And then later on, we might look at further subcomponents within this, but for now, it suffices to call this whole very complex perceptual process letter identification. From there, letters access an orthographic lexicon, and this is a difficult concept for students to get initially, because we tend to think, look, a word, if you're looking it up, has to have a meaning, and the word and the meaning is the same thing. But it's not true. If you look at the model, we distinguish the meaning of the word in this little gray triangle or this diamond-shaped box called the semantic system. We distinguish the meaning from the letter sequence that makes up the form of the word, and that is stored in the orthographic lexicon. So let me try and make this clear with an example. Supposing instead of seeing print, you saw the sequence BOOK, or book. That sequence, the letters BOOK in that particular order, that sequence is stored inside the orthographic lexicon, along with thousands and thousands of other words that you have actually memorized. And you may say, hey, I don't have didn't go and learn these words in the way that I try and remember a shopping list or some other kinds of objects. We are not saying that this is a conscious mechanism. This mechanism stores orthographic forms, and as skilled readers, we have thousands of these. From the orthographic lexicon, which is just the letter sequence itself, not the meaning is over on the left, inside the semantic system. So from the letter sequence, you then access the pronunciation inside the phonological lexicon. So the sequence BOOK in English is pronounced book, and we know that pronunciation because the sequence BOOK B-O-O-K, represented inside the orthographic lexicon, has a pronunciation book inside the phonological lexicon. And indeed, every word that you have a pronunciation for is stored in the phonological lexicon. Now let's go over to the right side of the diagram and look at what we mean by grapheme-phoneme conversion rules. This is another modular system, separate from the first root that we've spoken about, and that retrieves the pronunciation of a sequence of letters using rules rather than word identities. So take book as an example. We identify the first letter as B associated with the sound B. The sequence O-O-K is pronounced ook, and we put the two together using these conversion rules and we say book. That's the second root. Over on the left is the semantic system where the meaning of the word is stored. So let us now ask this question. Given a sequence of words, book, leopard, pint, hand, how does the system work to identify the pronunciation and the meaning? Well, take book, for example. We look up the word inside the orthographic lexicon, we find it, and we proceed to the phonological output lexicon where we find the pronunciation and we say, finally, out pops the speech output and we say book. At the same time, we understand the meaning of the word. Book is for reading, leopard is a dangerous feline, predator, pint is a measure of volume for liquid, body part is a hand. Those are the definitions, and of course, I'm not asking you to infer for 1 minute that that is sufficient in terms of what the semantic system represents. I'm giving you a toy view of some of the characteristics of the meaning that is represented in the semantic system. Now, on the other side, on the extreme right, we take the word like B-O-O-K, and as I say, we use these little subword units to convert the sequence book into a pronunciation. O-O-K is pronounced ook, B is pronounced B, and out pops B-O-O-K. Notice, most interestingly, that the two roots work together to produce the same pronunciation. The orthographic lexicon looks up B-O-O-K, it exists, it finds the pronunciation book, out pops the speech output book. At the same time, and quite independently, the grapheme to phoneme conversion system looks up O-O-K as a pronunciation. It knows that O-O-K in all English words, as in book, cook, look, took, and so on, is pronounced ook, B is pronounced B, and it also says, hey, that says book. Okay. So we're going to call the first root the lexical root, which is going from print to letter identification through the orthographic lexicon to the phonological lexicon. That is the lexical root. And the second root is called the non-lexical root because it does not require words as particular forms to be looked up. It is subword units that are used in the non-lexical root in grapheme-phoneme conversion. So notice because of that, because grapheme-phoneme conversion relies on subword units, it can read any word that is pronounceable, even meaningless words like V-O-O-K, vuk. So it is indifferent to what we call the lexical status of the sequence. So long as the word is pronounceable, it will produce a pronunciation. So vuk has no representation inside the orthographic lexicon because it does not exist as a real word, and any skilled reader will take a minute to look at V-O-O-K, and after a split second will say that does not exist as an English word, but I know how to pronounce it using grapheme-phoneme conversion rules. On the right, it is pronounced vuk. Now we come to an interesting question. What happens if this root truly existed and it was damaged or badly damaged? Well, you can see straight away that vuk no longer could be pronounced because I do not have these rules in place anymore to pronounce it. The million-dollar question, though, is what about book? Well, book will still exist inside the orthographic lexicon, so I can read that. So book will be read, if I damage grapheme to phoneme conversion rules, book should be read perfectly intactly without any problem, but vuk should not be read. And in fact, the patient should say, I just don't know how to read that one, but vuk, that is, and read book quite easily. Now, what happens if instead I damage the orthographic lexicon and grapheme phoneme conversion rules are intact? So I've damaged the other branch of this hypothetical architecture. Well, let us take leopard as an interesting case. How would the system cope with reading leopard? Well, leopard is not represented in the orthographic lexicon anymore because it has been damaged. Will grapheme to phoneme conversion rules succeed in reading leopard correctly? And the answer is no, because leopard is an exception word. We do not pronounce L-E-O as le, we say Leo. And so this system would read leopard as leopard. And we call that a regularization error. A regularization error, it's taking an exception word using grapheme to phoneme conversion rules that are intact and incorrectly assigning it a pronunciation which is incorrect given it's the fact that the word is an exception word. Pint would also be read incorrectly. And can you think for a minute why? The answer is that INT in English is pronounced int. So we have hint and lint and flint and stint and mint, and PINT, pint, is an exception. So the regularization of pint, if you have damage to the orthographic lexicon and you cannot find that word inside your orthographic lexicon because the lexicon is damaged, if you then relied on grapheme to phoneme conversion rules, you would say pint, and we call that a regularization error. Finally, hand is not in the orthographic lexicon if it's severely damaged, but grapheme to phoneme conversion rules will correctly pronounce H-A-N-D as hand. And so in this sequence of words, damage to the orthographic lexicon would produce correct performance on book, because book is a regular word. O-O-K is ook, as in book, look, cook, rook, and so on. Leopard is an exception word, so the system, if the orthographic lexicon was damaged, would fail on leopard. Pint is an exception word. The system would read it as pint. And hand would be correct, again, because grapheme to phoneme conversion rules correctly can produce the pronunciation of H-A-N-D. So supposing I had two tasks. One task is reading aloud nonsensical words which are pronounceable but have not no meaning, but are not represented in the orthographic lexicon because they haven't been seen before and you haven't stored them then as visual words. And task two is to read aloud unusually spelt words, or not unusually spelt, but unusually pronounced words. So they have perfectly okay spelling patterns, but they're unusual. They're unusually spelt in the sense that they have unusual pronunciation. So pint is unusual because it should have been on the basis of rules pronounced pint. Ache is unusual because it should have pronounced atch on the basis of rules. B-E-A-D should have pronounced bed as in head and instead, and read as in I read a book yesterday. B-O-T-H again is exceptional because it's not, according to rules, it should be pronounced both, not both, as in moth and cloth and sloth, etc. Now, supposing I have these two tasks and I have a patient who has damaged grapheme to phoneme conversion rules. And again, remember, I don't have evidence yet that there is such a system. I am making a theoretical claim that has to be tested on the basis of performance. And if such a route does exist, the non-lexical route, what do you think would happen to a patient who has lost grapheme to phoneme conversion rules? Well, this task should be damaged, the ability to read nonsensical words, because these words have no representations inside the orthographic lexicon. You need grapheme to phoneme conversion rules to read them, and you don't have them. So the patient will fail to read yint, goop, saif, lunk, etc. Reading of words in task 2 should be fine, because they have lexical representations inside the orthographic lexicon. That is still preserved in the patient, and the patient should read pint, ache, bead, etc. quite well. What happens, on the other hand, if the orthographic lexicon is damaged, but grapheme to phoneme conversion rules are intact? Well, now, the patient should read nonsense words perfectly well using the non-lexical route. So yint, goop, saif, lunk will be read correctly, but the words in task 2 would need to be looked up in the orthographic lexicon. They don't exist because of the damage there, so the patient will regularize each one using the grapheme to phoneme conversion rules by reading pint as pint, ache as atch, Bead as bed, both as bath, etc. And in fact, both of those syndromes, so task 2 will be impaired. In fact, both of these, and task 1 is okay. Both of these syndromes exist, and we have special names for them. So phonological dyslexia is impairment to the non-lexical root. Surface dyslexia is impairment to the lexical root. And the two syndromes together provide evidence for the two components of the reading system. Remember that if we say that you're impaired, we have to say impaired relative to something else, relative to some standard of performance, and that performance is always a group of normal control subjects. So when we say task 1 is okay, what we literally mean is that the subject will read these words, or nonsense words in this case, as well as normals. If task 2 is impaired, it means that relative to normals, the patient is, and the normals would be age-matched controls at the same level of education and socioeconomic background, etc. But if you're impaired relative to a normal control group. So phonological and surface dyslexia together make up what we call a double dissociation between the lexical and the non-lexical reading root. And the existence of these two reading disorders provides evidence that these two roots are separate functional components of the reading system, or separate modules or modular systems. And another way to state this is that the lexical and the non-lexical roots are doubly dissociable. We can impair one and not the other.